All right. Let me just finish putting this back to where you guys should be, and then we'll uncomment some stuff when I get to it.
There's like already an end
Oh.
in line 96. Yeah.
Oh, thank you. Then we're good. Well, we're not really good. Now we're good enough. Okay. So let's go through some of the things that we needed to do here. So last time we talked about wrappers. We talked about frame buffer. So let's look at a couple of our things. So we had to put our wrappers allow us to take assembly code and wrap it inside of a C function, right? So what we did is we added to our linker. So here's a link file, io.s, this global out B. So here's the assembly, this is the label for the assembly instructions to move something onto the stack. So taking parameters and moving it onto the stack. Does that make sense? So we want to write something out. So we're going to move the data to be sent onto the stack and move the address of where we're sending it onto the stack. And then this actually sends it to the IO port. In this case, we're going to the screen. Okay, and we haven't done anything with in yet. So in is just sitting here without us using it yet. All right, so this is assembly code that does some of these things because out and in are assembly code functions that are built into our processor, but not built in, we're writing the operating system, right? So we don't have these, we can call them system calls at this point in time. All we have is the things that our processor knows how to do, the magic tricks of our x86 processor, and we know about the registers of the x86 processor, and we have told Box here, this dude, that our machine has 32 megabytes of memory. All right, so we have a processor that is connected via the memory bus to 32 megs of memory. Okay. Now, we're using this VGA ROM image. So this guy is what gives us that basics. I brought up a page here we'll talk about in a little bit that kind of tells us where's that starting location for our frame buffer. So we want to put ourselves, we want to go back in time to the folks that might be writing operating systems in the very early days of personal computing, let's say, and they are sitting there and they have a CPU that knows how to do some magic tricks sitting there. They have some memory, in this case 32 megs of memory available to them. Maybe they decide, almost think about this in terms of if you're a game writer for like PlayStation or Xbox, when you are targeting a set amount of hardware. Things are a little bit looser than that now with like PlayStation 4 Pro and crap like that. But let's just roll back in time a little bit and say, if you were writing a game for original PlayStation, every single original PlayStation had the exact same hardware, right? That was what you were targeting, is that hardware. That processor, that amount of memory, the IO ports, all that stuff, okay? So that's what we're doing here. We're saying, okay, well, we have a processor, and then we have this much memory. Well, how much memory do we need to presume every machine will have, and then how much of this is just extra? All right, so in those early days, we might say, okay, well, one of the things we're going to let our VGA BIOS know is that they can go and check a very specific part of memory for data it wants me to show on the screen for the frame buffer. Okay, that's where we came up last time with that, let's see, what is it, or K-main? Yeah, forget about this for right now. I'll come back to that. So this guy, B8000. This is the starting location for our frame buffer for, what is it, CGA? I have it in here. I think I opened up a thing for it. So this is vintage PC stuff. for CGA. So we have multicolor, but not high definition type color. This is going to be stored in B8000 to BBFFF. All right, so it's saying here is the part of memory that we are saying is reserved for my frame buffer. Nobody else is allowed to use this. Well, if they want to use it, fine, but you're going to get some weird behaviors because I have specifically, think about like you're farming in your yard and you've set one area aside for tomatoes and another area for something else. We've set this part of memory aside for our frame buffer and said, don't put anything else there, because if you put other stuff there, we've designed our BIOS, our VGA BIOS, to automatically keep coming back and checking that place in memory and making the screen look like whatever that says it should look like. This is a hard-coded decision that we made in early PCs. The same kind of decisions get made today, right? Or at least with some sort of offset. Maybe the operating system gets put somewhere in memory and then everything is some base offset off of where the operating system starts. And we have some sort of minimum requirement for memory in our computers for our modern operating systems that say the OS will run in its most primitive state in this amount of memory. If you want to do stuff beyond that, i.e. you want to store data and crap, that has to be outside of that reserved place in memory for you to be able to accomplish things. Does that make sense? All right, so we've kind of built a sandwich here. If we, let me go. So we're going to draw a picture. All right, so what we have here is we have an amount of memory. I'm going to make this guy red. That's reserved for the operating system. I'm going to make it relatively short. I'm not even sure exactly what that is by default. It's going to be something defined in our... RC in this guy, and also something that Grub will set up for us. Grub's going to say, hey, I'm your loader that's going to take from the BIOS to a running operating system, and we're going to reserve so much of that memory for the first parts of your operating system. Whatever it is, I don't know what those things are off the top of my head, but we're just going to say the first portion of memory is for that, right? Similarly, we have the last 4096 of memory is for what? What goes there? We defined it in our original linker file. This is our stack, right? So we go to the very end of memory and we work backwards from our stack. All right, so that means we have space in between. Put a little gap there. All right, so we'll call this unused memory. So this is memory, and again, we don't know how much of this is taken up, so we're just gonna make a guess. I think I bumped mine forward 2 megabytes and just decide, who needs the first 2 megabytes? We'll just use the rest. So this is 4 megabytes, right? 4 megabytes of stack space. This is 2 megabytes, so we're saying 6 megabytes is 4M or 4? Yeah, this is 4K. Okay. 4K so yeah, so this is 4096 bytes or 4 kilobytes of stack space. All right, and I'm presuming 2 megabytes of space there, but I legitimately just guessed. We're not going to touch the first 2 megabytes because Box might want to put stuff there. Their version of the x86 BIOS, and then whatever Grub's going to use. Okay, if you remember, Grub loads itself into megabyte number 1. Okay, so we're at the very least, Grub is showing respect to the first 1 megabyte, and then I'm giving Grub the second 1 megabyte, and I'm just saying everything else starts at megabyte 3. Just 'cause.
Seems like you're wasting a lot of memory.
Potentially. Potentially. But we still have plenty of memory here. So if we are operating off of 32, if we're operating off of 32 megs of total memory, and now I'm operating off of 30 minus 4K, I still got most of my system memory for data stuff. We're just going to call that okay. Now, as we go through here, we might bump into other things that, unbeknownst to us, Box is using. You know, there might be some wiggle room in here that we don't think is currently being reserved, but it is being reserved. Let's just say. But we're going to call this the space where we get to put stuff. Go ahead.
So you're probably about to get to this, but why B8000? It seems like a rather arbitrary address.
Yeah, I don't know. I don't know why they originally picked that, but that's not a Box thing. That's a early x86. Maybe it's for the size. Maybe it's for the stuff that comes before it. Chances are there's reserved memory chunks prior to that, and maybe that's just where they get left off.
Okay, I didn't know if you knew or not.
No, not for a particular. Yeah, that's just the value it's historically used. Today we don't use frame buffers in our modern operating systems, but you know, this is going to be good enough for us. All right, so this is the memory we have that we're going to have to work with. So this is kind of where we're going a little bit later on in class today, but initially we don't have to worry about this. All right, so come back into here. We have an operating system with 32 megs of memory, and these are the rules we're playing by. Specifically, the VGA BIOS sets up the rules for our frame buffer. All right, so let me go into io.s. We saw this already. So this is our functions written in assembly, which are using the stack. ESP points to the end of our stack. So if I go ahead and just kind of draw that picture, this is our stack pointer. And this guy points to the end of that.
So by doing chapter 3, now we have ESP.
Exactly. Give me a second. All right, so this makes sense, and then the stack works backwards. So as we push stuff onto the stack, it works from here towards, so we've reserved 4096 of the last part of memory for our stack. And our stack is where variables and things, our parameters get pushed onto. We saw that happening inside of our file here where we were moving whatever's on our stack into this register. Another thing that's on our stack into this register. So our stack is 32 bits big. Right, so this is the second element on the stack. This is the third element on the stack moving into these registers. And that's for out. Similarly, for reading something in, this is move the address of where we're going to be reading in from, which is going to be the second element on the, well, the first, not the first real value on our stack will be the thing we just pushed on, which will be at the top of the stack plus 32 bits, 4 bytes. So we'll move what I'm going to read in from into DX, and we haven't used this yet, but we're going to try to use this hopefully today. So where are we going to read in from? And then we're going to read a byte from that, storing the result inside of AL. Right, so that's going to be the 1 byte of memory we read in, and it's going to be in AL. That's the low 8 bits of the 16-bit register AX. That's when we go to read something in. So reading in bytes is going to be like reading in a character from the keyboard, for example. We might want to type and have whatever we type show up on our frame buffer. That might be the go-to move we want, right? So we might put our cursor somewhere on the frame buffer, and then we start typing, and we see whatever we're typing show up on there because we're reading in from an input port and writing out to the frame buffer. Make sense? All right, so, but again, these are functions that we need to wrap because we need to, at the assembly level, at the low level, we need to talk to our x86 processor. And because we're writing our own operating system, we don't already have system calls for doing this that do it for us. So that's why we put in our linker our middle language, which is our low-level language that a compiler typically would output. We're putting that in there, and then we have our io.h, which provides for us the wrapper functions. So out B, the thing that we defined as a global in here, is a function that takes in two parameters, a short and a char. Here's my char, here's my short. Short is 16 bits. Make sense? And it loaded it from right to left, so top of my stack is the short, then it's the char, the byte. How do we know that this is a byte? What aspect of what I have highlighted there tells us that our stack pointer plus 8 must be a byte?
Well, because we're moving it into AL, which is the lower byte of a 16-bit register.
Yep.
So even if we have a value that's more than that, we're pushing 9 bits into 8 bits. At the end of the day, we're only going to have 8 bits.
If this guy is a gallon of liquid and I'm pouring it into a glass that can only hold a cup, it's going to overflow. But we're going to presume that whatever this guy is will fit perfectly, or at least fit within the confines of AL. And AL is the low 8 bits, a low 1 byte of a 16-bit or a 2-byte register called AX. So we know this guy must be 8 bits because we're putting it in a container built for holding 8 bits. We know this guy must be 16 bits because we're putting in a container capable of holding 16 bits. If I go over to io.h, what's that short? Here's a short. A short is a 16-bit value. An int is a 32-bit value. So here's my short. Here's my char. Okay? So this guy wraps that assembly language, and what will end up happening when we compile the C program is it will create that low-level code that will take this guy and push it onto the stack, and then this guy and push it onto the stack. And we've defined with boxRC, we've defined in our loader how big the stack is, and then this will place it at the pointer for our stack at the end of memory. Go back here. So the compiler will do the magic of wrapping this for us so that we can call this function, and it will call the assembly for us behind the scenes. Similarly for in, we just want to know where are we reading in from. We'll worry about how do we get that value later. Okay, so going back to, let's look at our makefile now. So in our makefile, we have to add in io.o. Okay, so this is one of the files that we want to link now. So make sure that that is added in there to your makefile. Let's see, any other changes we need to make here?
That was the only one.
Okay, so that'll update our makefile to work for that. In our loader, I don't think we needed to make any changes. One thing, if you look in your loader, this was something I think, did you ask last class, Blaine, whether we need a main method? So if you think back 2 classes ago when we were just doing our Cafe Babe thing, this is what our loader does. Our loader positions our stack pointer correctly. Then we moved into EAX, which is a 32-bit register actually. AX is the 16-bit, EAX is the 32-bit. We moved Cafe Babe in there.
Does the E stand for extended?
I think so.
Neat.
EBX, we just put in a 4. This was just us proving that we could do other things in here. So we don't even need this Cafe Babe thing anymore. I can just take that out. That was meaningful stuff, right? Or meaningless stuff.
But how else will we know it's our OS without Cafe?
Well, now we have a frame buffer output. See, we don't have to check the state of registers anymore. Okay, but what we did need to add was a call to our main method. All programs begin and end with main. Right? So all programs begin and end with main. So this guy says call main. So inside of kmain, we'll look at the other stuff up top here in a few minutes, but down here I have my int main. And what I'm going to attempt to do here is I'm going to try to write, forget about this number here. It's an offset thing that I'm going to be talking about in a little bit. So yours probably doesn't have that. But we're going to write an A in green foreground color and dark gray background color, I think is the parameters. And then we're also moving the cursor around. Don't worry about that right now either. Those are the 2 things we're going to try to do in main. So when our loader says call main, it's going to start at the beginning of main and do whatever main says to do. Go ahead.
So this is kind of, I guess, a bit more of a design decision. But after we call main, we do some stuff. We return 0, go out to loader.s, go into loop, and then we loop infinitely. Would it make more sense maybe to have that kind of loop in the main function itself and not have that little loop in loader? Or
well, I don't know if it makes more sense. I mean, I think at this point what we're
would
doing,
that be like a valid thing?
it's equivalent. Yeah, for right now.
Right.
But if main is set up to kind of drive if we're just thinking ahead a little bit, if main's set up to drive like a command prompt, we probably do want it to keep calling main over and over again. Why put extra burden on efficient assembly when our assembly says do this stuff, then loop it and do it again? Loop it and do it again. That might give us the ability to clear out the frame buffer and do all sorts of other things. Not that we couldn't accomplish that by just writing our own infinite loop in main. But if by doing that, we're probably leaving our memory potentially vulnerable if we just shut down the computer, I guess, but it wouldn't matter anyways.
Okay.
So we don't have a great example against it right now.
Right.
All right, so this is all we're going to try to do in main is write an A out and then move our cursor. But we don't even need to do that if we don't want to right now. Okay, so we're just going to try to write an A out to the screen. Now let's look at our supporting cast up here. So notice that main is including io.h. So that means it's bringing in our wrapper functions. These are C functions that we have access to now in main, which wraps around our assembly code from our linker file. All right, and we're defining a whole bunch of constants here. Just these are the numbers for our black, blue, green. You know, these are just hard-coded values that were from the chart we looked at last time. And then we've decided, okay, well, we're just going to give ourselves a little pointer to the beginning of our frame buffer because that might be helpful, right? I remember what our frame buffer was last time. It's what, is it 50 by 80 or is it 80 by 50?
80 by 25.
80 columns and...
So 80 columns and some number of, so that means we would have 80, you think it's 25?
I remember it was 2,000.
All right, so 2,000 total length?
Yeah.
All right, so 80 by 25, so that would give us 25 rows, 80 columns per row, where each cell is holding, what, a double byte? Is there one byte for color and one byte for foreground, one byte for, no, a byte for the value, and then a byte for, well, a nibble for the foreground color and a nibble for the background color.
Yeah.
Right? Nibble. The. She was head bobbing a second ago, so now she's woken up. We're going to exercise and stretch. All right, so that means that each of those columns are a 16-bit step, right? Because to define what's in, they're calling it a cell in our like write cell thing. Each cell holds 16 bits of information. The first 8 bits are the character we want to write, the ASCII code for the character. The second 8 bits are going to be the foreground and the background color. So 4 bits each. 2 nibbles equals a byte. All right, so that means that we can think of our frame buffer as kind of like a 2,000 bucket array. That makes sense? It's a 2,000 bucket array. So actually, with that in mind, we're going to want to revisit this because of what we're storing there, I actually don't think this is accurate. The base address is fine.
I think we need like.
It needs to be either a short pointer or we need to treat it as the double hop. So we'll see in a bit. I already do that in mind.
Do a UN 16.
Well, that's fine. I think the idea here is that they're trying to show it as a character that lives there. But each character that we write actually will have an extra byte following it that dictates its color. Foreground and background color. So that 2,000 thing we're talking about here, that's 2,000 total bytes. So that is, well, no, it's 80 times 25, so that's 2,000 total cells. Where it's 4,000 total bytes. Because those cells have 16 bits of data in them. That makes sense? The first 8 being the ASCII value, the second 8 being the color. So this presumes this 25 rows is accurate. So it's 80 columns by 25 rows. I don't know if that's accurate or not, but whatever. We have a frame buffer that every 160 bytes will kick us down to the next line. Does that make sense? All right, so we're keeping track of the base address of our frame buffer. That's what that does. Where our frame buffer starts. Okay, and then we have this function called FBRightCell. This guy is going to take in, don't worry about this. I'm treating this as like this offset thing. I'll talk about that later. But it's taking in a character, so a 1-byte character, and then it's taking in a foreground character, but actually, so a foreground byte, but actually only the 4 bits of that are being used. And this is a background byte, but only 4 bits of that are being used. That's why we shift the first one over 4 to give us the high 4 bits. And then the other one, we zero out to ensure it's zeroed out the low 4 or the high 4 bytes, high 4 bits, leaving us the low 4 bits for the other half of our value. Then we exclusive OR those together, or I'm sorry, we bitwise OR those together, giving us a single 8-bit value with the high 4 bits being the foreground color and the low 4 bits being the background color. That's what I have highlighted there does. It merges these two values into an 8-bit number defining foreground and background color. And then we're putting that along with our actual value, C. So we're putting in at byte I, where we're putting this, variable C. Then we're putting at byte I plus 1, the color of that character. That's our 16 bits for each cell. Make sense? So that's what this FBRightCell does. So then down here, I'm going to try to write out an A with these different colors. So we'll do our make run. Oh, comment problems as I was fixing stuff.
You never end that other.
I think it's just wanting you to give a second
Oh.
start in there, like on line 96.
We'll just do this. Continue. All right, and there is our A up there. What is interesting is it does have a little bit reverse, because didn't I have my foreground color being green, my background color being gray, but it actually has them flip-flopped here. We're having Wi-Fi issues.
Wi-Fi's been crappy for a while now. Everybody's complaining about it.
Yeah, it has.
All right, so in any case, we now have a single thing printing out there. So that was what we needed to accomplish for today. All right. So now let's take our next step. We're going to write it the wrong way first, just so we can see the example here, because this goes back to what we were talking about here, where there's a portion of memory that's already reserved, another portion of memory that's already reserved, and now this is our place in memory. Now we might be tempted to come in here and say something like, well, actually, let's just write it. I'll just hard code it in here for right now. So we might be tempted to say char pointer s is equal to hello, something like that. Define a string. All right. Now I might want to say for int I is equal to 0, I is less than, I'm just going to hard code in a 5, I plus plus, and then what I want to go ahead and do is I want to write instead of, well, I'll write out at bucket I, at position I, and the value I'm going to write out is S at bucket I. So it should be H the first time, E, L, L, O. And this, we would hope, would write it out. I'll go ahead and save this. So we're not even using our write string thing here yet. We're instead just saying, hey, look, I have 5 characters. I've proven I can write 1 character. I'm going to go ahead and try to write 5 of those guys. All right, and it's telling me that I have an unsupported executable format. Why is that? My compiler worked. It gave me an output, but it gave me an output that was based on a architecture. Good.
Isn't it writing for single member address?
Well, this is a chicken or the egg problem. So when it compiled this for me accurately, what it did is it assigned string literal memory space to that guy, right? We have that memory that we don't know, that we know we have available to us. We don't know how this guy's being used, but we presume that our x86 emulated operating system running in box probably uses this space differently than a modern Linux-based operating system. Because what does a compiler do? A compiler says, we're asking you to go through and give us the equivalent assembly code for this stuff. And part of what C says is if you just give me a string literal, I'll go get you string literal memory space. Not paying any attention to what that memory space might mean in whatever machine you're targeting. Right? So this guy has memory, but it's probably accessing memory that's far outside this, or it's flagged itself as a executable, an ELF file that isn't compatible with the x86. Go ahead.
Well, I got to what I was going to ask about it probably going outside, but does that mean that we could get lucky and sometimes it could run?
Probably not in this particular case because where string literal space likely exists, but in the big scheme of things, there is a situation where we could get lucky, and the memory that you get might just happen to be okay memory to use. You might set up your campsite at some unused plot of land, and you might be able to live there for 20 years if nobody ever breaks ground and builds a house there. It might just happen to work out. Nobody else wanted it. Nobody else was using it. You laid claim. Well, okay, so like in Java, if I define string s equals hello, that string gets put somewhere in what's called literal memory. So there's a place of memory blocked off by the Java virtual machine that says, I'm going to store all of your literal values for you here. If you try to store the string hello again, rather than storing it a second time, I'll have both of those guys point to the same place in literal memory. This goes back to our lesson in Java. Here, let's show it to you real quick. Yeah, this is fine. So I'll do vi test.java. All right, so if I say string s is equal to hello, and then I say string s2 is equal to hello, and I say, I'll fix that, string s3 is equal to new string hello. And I do a system.out.println s equal s2, I'll get a true. If I do a system.out.println s equal s3, I'll get a false. System.out.println s2 equal to s3, I'll get a false. Reason being is that when I say string s equals hello, I'm just giving it the string literal hello here. So it's going to go and find a home for this in this reserved space in Java, the Java virtual machine, for literal memory, for values to be stored. Like 0, 1, 2, 3, all those digits are there. Our Unicode character set's there. And now we can store some strings there as well. When I tried to use the hello string literal a second time, it checked that literal space and says, oh, you already have hello stored in literal space, so I'll just go ahead and let s2 equal the same memory address as s held. That's why s equal to s2 will return true. This memory address is equivalent to this memory address. It's not comparing the contents of hello. When I say s3 is equal to brand new memory that I happen to want to have hello, at this point it's not using string literal space, it's using data space for the user, probably heap space. And it's saying, here's some brand new memory that the user has requested. I need enough memory to hold this guy. So it's going to put that guy there in memory and return to S3 the memory address where that new string was created. So even though it's still the same contents, hello, it's S3 holds a different memory address than S2. S3 holds a different memory address than S. So there's our true, false, false. Go ahead.
So I'm decently certain on this being a kind of feature of the JVM, which isn't really
A decision of the
Right.
JVM.
And that's not defined in the C standard, but I'm guessing that GCC says, yeah, that's a good idea. We're going to compile it like that just because that's more efficient.
Well, but what's the Java VM? When we say Java virtual machine, we expect it to be kind of a virtualized processor as well as kind of a minimalistic Java operating system that knows how to do I/O stuff and things like that. So it's made those decisions of what part of the memory that in this case, the Linux operating system hands the Java virtual machine. Will the Java virtual machine set aside for literal space, set aside for heap space, set aside for stack space? You know, how am I going to divide up memory, and what's the user allowed to use, and what is the virtual machine reserving for their own magic?
Okay.
You know, because they got to give themselves enough elbow room to do all the tricks that they want to do.
Right.
Does that kind of make sense?
Yeah.
So here in C, I'm effectively asking our operating system to tell us how to treat a string literal. We haven't taught it how to do that. Make sense? We don't know how to deal with string literals. We can deal with char arrays, but this type here with double quotes around it isn't something we've defined meaning for. So now, having said that, can I do something like char pointer S? So here might be the, I'm just going to write in the code here because it's not going to work anyway, so I'm actually going to run it. So can I say char pointer S is equal to malloc 5 times size of char? Can I say go find me some memory big enough, so allocate me some memory big enough to hold 5 times of size of char? Well, malloc is going to be mapped to a system call on the operating system we are building our executable for. Remember, compilers, we're using GCC here, right? Or we're using CC, I don't remember which of the two. But we're using a compiler. Compilers target two things. They say, what's your architecture you're targeting? So we're targeting the x86 architecture. Actually, I think we say i386, which is the closest we can get to the x86 architecture in a modern compiler. So we're saying I'm targeting an old architecture, and I'm targeting no OS. That's what we're compiling for. But under normal circumstances, if I'm writing a C program and I compile it, I'm saying I'm targeting the current architecture, which will be AMD 64 or something like that, the 64-bit Intel compatible architecture, and I'm targeting the Linux kernel and all of its famous system calls and know-how and how it manages memory. And so when I say malloc, I'm saying Linux, give me some memory. Just like the new keyword in Java, I'm saying operating system or fake operating system in the sky, Java, virtual machine, go and get me a memory to hold this guy. And it's just magically coming out with a memory address saying, hey, don't worry where I got this, but you're allowed to build here. That's what it's doing, right? But we aren't using that second piece here. This goes way back to, remember this would have been one of your first programming classes, right? If I had something in here, let's see, hello world Linux assembly. Yeah, remember this guy a long time ago?
No. Yep. Not nearly as long as I remember it being.
Well, because this guy is using power tools. This guy is showing us how to talk to the Linux operating system in terms of the Intel assembly language. Okay, so it's saying, hey, I'm going to move 4 values into very specific hardware registers for seemingly no reason. And I'm going to put a 4 into EAX. I'm going to put a 1 into EBX. I'm going to put the message I want to print out into ECX. And then I'm going to print my length into EDX. And then I'm going to go ahead and let the operating system take over. Have the kernel. What does the kernel do? It runs and looks at EAX and says, you want me to perform my super power trick number 4, which happens to be syswrite, which I promise you is way better than us writing to our frame buffer, especially only be able to write one character to our frame buffer as we can right now. But this guy knows how to write cool stuff to the screen, right? Okay, but the point is that that's something built into the Linux operating system that we can leverage now in assembly because, hey, they say, look, we wrote the C code called syswrite. That's our goal in here, isn't it? We like to write C as often as we can and only have to dump down to assembly when it's absolutely necessary. Every now and then we'll write some assembly functions to give us just enough hook into the processor for us to do some high-level stuff that we might want to do in bulk. But do we imagine as we move forward, we're going to have to still write plenty of stuff in assembly just to give ourselves some level of convenient access to the registers and things like that? It's going to keep happening, but we'll continue to wrap that stuff in, for instance, a function like syswrite, which we believe underneath that is some scary, scary stuff, right? So syswrite's going to say, okay, that's what you wanted me to do. Where do you want me to write it out to? So I'm going to go and look in EBX. I find a 1. 1 maps to Linux's internal decision to write stuff to standard output. That's what a 1 means to Linux. Standard out is 1. That's our monitor. Great. Okay, what do you want me to write? Well, I'll find that in ECX. This will be the base address of the string that you want me to write. And then how long is it? So this syswrite is taking 4 inputs. In this case, not even using a stack, but it's taking 4 inputs, and then it's going in and writing that out to the screen using this power tool right here. That make sense? But it was able to do that because we compiled for, this outputted code here was compiled for the Intel architecture running on the Linux operating system. We targeted both of those truths, and that gave us low-level code that leveraged the system calls of the Linux operating system. When we're compiling ours over here, we're saying, look, I'm using the x86 processor, or the i386 processor, an Intel processor, an old one, and don't compile for an OS, because I don't have one. Why don't I have one? Because I'm in the middle of writing one. Does that make sense? So a lot of things that we take for granted as just being available to us are actual things that these operating systems that we've probably devalued over the years as just being, oh, you know, Microsoft, they suck, they did this, that, and the next thing, and everything breaks all the time, or the Mac OS operating system blows, whatever it is. You know, we sit there and complain about something that is effectively allowing us to be computer scientists. That make sense? So that OS does a lot of stuff for us. So in this case, it's hamstringing us, right? In this case, we're saying, look, I really want to deal with strings. Yeah, see, that's something provided to you by your operating system. Okay, fine. I want to ask you for some memory. Yeah, that's something else that the OS gives you. You want memory? You give yourself your own memory. Back to this picture right here. How do I assign myself memory? Does that make sense? Now I can go ghetto style with this, is what we're going to do at the beginning here. So I just came up here and I said, you know what? I'm going to start off my pointer to the beginning of the space that I own at 3 megabytes. Just 'cause. So here's my data space start. That is very interesting. Look at all the stuff it just wrote out. Must be the XML data for whatever that guy is. Okay, so now I've given myself a pointer. And I've just arbitrarily decided that this guy points to the beginning of my unused space, which is at megabyte 3. So that means everything before that is reserved for the OS and its mysteries. Okay, this is my loader, this is the BIOS and the things that it's going to do in just this default way. You know, how it's going to use my system's memory and things like that to get my OS launched. All right, so I'm going to say, look, here's your playground space. I'm giving you that, whether I've given it too much, whatever, who knows. But I'm going to go ahead and I'm going to pick up, for all we know, we haven't given it enough. We're going to run into some issues moving forward. But we said, you know what? This is where my data space starts. And for right now, we're just going to kind of hope that we don't fill this up and start intruding on our stack. All right, because we're not writing a real commercial grade operating system here. We're kind of like flying by the seat of our pants. Okay, we're saying, look, I need to store memory. I need to store values, namely a string, whatever that is. So really, I need to store a series of characters, right? And I'm going to put it here in my memory where I've deemed it available. Okay? So that's what I'm doing right here. I've just arbitrarily, and I don't like the way that's written, I like to put the pointer with the type. There isn't it, it's just a syntactic preference. I like to think of variables as being the name of the variable, the type of the variable. The type of this variable is a char pointer. So that allows you to think about it consistently throughout when you start putting spaces there between there. C doesn't care, but now you've kind of separated the pointer part from the char part.
That's loud.
Oh yeah.
It hurts. That is.
All right, so I've just decided to hard code inside. So data space is a variable capable of holding a memory address of a char. And I went ahead and hard coded it to this memory address. Because I can, I think. There's my picture, my OS. I'm just saying I am pretty sure we're safe starting here. And I'm pretty sure I'm not going to do something that complex yet where I'm going to start running into my stack. But soon, maybe, I'll have some really hard to find bug because I'm overwriting part of my stack, or I'm using memory in here that maybe wasn't quite as available as it seemed. So we'll find that out because I haven't found a great box documentation for their BIOS or their VGA. It's a little bit sketch. So we're just this kind of guesswork at this point. But this isn't any different than the early operating system designers would have been going through, other than the fact that they probably had a little bit better specifications for what memory components their BIOS was using. You know, instead, we're just going to keep putting stuff in there until it doesn't break. And like, this is a good starting point. Does it break after this for a little bit? Nope. I think we're safe. You know, it's kind of like, walking blindfolded and barefoot through the rattlesnake nest. Do rattlesnakes have nests?
Yeah, I think so.
Sounds like they should.
It sounds like I think they do that.
All right. So this makes sense what we're trying to accomplish here? All right. So I've just arbitrarily decided, and all these are base addresses. This is the base address, i.e. the beginning of our frame buffer. This is the base address or the beginning of our data space start that I just named. That's where the start of my data space is. Okay? So now I can do something like this. I can go ahead and give myself, so here, we didn't run it, but trust me, that won't work. I'm not targeting an operating system, first of all, but even if I were, it would be giving me a memory address that very likely is not going to line up with my safe space inside of my 32 megabytes of memory, especially considering that most modern operating systems are probably reserving the first 1024 megs of memory for system stuff. So we're using an extremely tiny OS mentality compared to modern operating systems. So if we're asking to allocate us some memory, it's probably going to get us something significantly farther down the street that's well beyond our 32 megs of memory. So we're just off the end of the street. We only have 32 megs. It gave me gigabyte 1.5, and we've died. We'll get a segmentation, something or other, or, you know, it just doesn't work. All right, so this guy is bad news bears. So I'm going to just steal this here for a second. Okay, so we'll get rid of this. So I want to create a string. And I'm going to go ahead and say this string is going to start off. I'm going to give it the result. We're going to pretend like we called malloc, asking for 5 times size of char, i.e. give me 5 bytes. That's what we're going to pretend like we asked for there. But instead, we didn't ask anybody. We're not even keeping track of it. We're just saying, look, this is a safe place to start. We're just going to hope nobody else is using it right now. Because we're not checking, we're not asking, we're just using. Okay? So I just arbitrarily set S equal to my base address for my data space start. As if that was the value that malloc was going to hand us. Just right there at the beginning. Make sense? So that's where our string is going to be. Then I'll go ahead and I'll start filling that string up with stuff. A string is a character array. So this is saying, here I'll write the second line a little differently here. So this is equivalent of saying the value that lives at S plus 1 is equal to E. So this syntax here and this syntax here are, well, this guy's syntactic sugar for this guy. This says go to base address of S, add to it 1 times size of char. Since it's a char pointer, it'll automatically take that size step. So now we're at a memory address, and the value that should be at that memory address will be an E. So you can pick which of those syntaxes you like better. Most people are going to like this one better, but understand that it's not doing anything special. It's just walking through memory by an address. Base address plus the number of steps from that base address. I want to go to bucket 1, so I'm going to take 1 step from the base address. I'm setting the actual value that lives there. So I'll say set star of that guy, the value there is equal to an E. All right, so now what I can do is I can say for int I is equal to 0, I is less than 5. I happen to know that I have 5 characters in my string. Good enough, we can count HELLO, it's 5. I plus plus. And each time through, I'm going to go ahead and I'm going to call upon my, I really wish I had saved that line. Somebody else can tell me what it is. FBRightCell. We're going to write it at position I. We're going to write S. Here, we'll do the cool kids. S plus I. And then what are my, oh, there it is. FB green and FB dark gray. For no good reason other than just that's what we've been writing. So I'm going to go through 5 times. Each time I'm going to write to a cell. What cell? Well, it'll be cell 0, cell 1, cell 2, cell 3, cell 4. What am I going to write? I'm going to write the value that lives at memory address S plus whatever I is. So this is equivalent of me saying that. Make sense? But it doesn't look as cool. Go ahead.
Would you have to do like I times 2 because you're
Taking jumps, yeah. Thank you. Remember earlier we said that our, actually, the answer I think is no, because I think I do it in here already. But you're right. I don't do it in here already. I do it in here already. I don't do it in here already. I do it in my other one already. Yeah, so the idea here is that, remember earlier we said that our frame buffer, they're not bite-sized steps. It's double bite-sized steps or word-sized steps. The first byte is the ASCII value. The second byte is the color. So I actually need to do steps of size times 2. So bucket cell 0 will be at 0 times 2, which is 0. 1 will be at cell 2, because 0 and 1 of the frame buffer were for the color and the value and the color of the first one. So this allows me to hop through at 2 byte little skips. So it's a skip or is it a hop?
Scott.
That's a half higher than mine.
Does it?
Does it?
No, actually, I think the skip is like
Imagine
distance
if your legs are
and
together
hop.
or something.
Okay. This would have actually worked without that on there. We would have just had every other character printed out. Because we were not writing to all the right places. We were writing to the first half of the frame buffer thing, so we would have gotten probably some funky colors and maybe some funky characters too. Okay, but in this case, I'm going to go through all the characters in my array. This guy. And I'm going to write at cell 0, 2, 4, so on and so forth, in green and dark gray. All right, so I'll go ahead and, I'm not in that folder anymore, am I? Ninja'd. S undeclared. Oh yeah, I'm just writing that inside of FBRightCell. Just wait, no, actually.
It's 89.
Yeah. I've given my method. Yeah, because remember earlier I said somebody will just tell me what I wrote when it was actually there. This line right here. I said, oh, I erased it. I didn't actually erase it. It's just up here. And I'm trying to access variables I didn't define until down here. So it's fine. Alright. Yeah, so there's my hello all the way up here. Huh? That's starting operating system is what it used to say there.
Okay.
But now I've replaced the star. Actually, might be loading. No, start. Booting.
Yeah.
It's overwritten the BOOT.
Wait,
Maybe there was a space before it.
there's a space.
Okay. Yeah, there used to be some more letters here, but I've overwritten those in the frame buffer.
I see.
And that's where my offset thing came from. So I can then decide. So it's what? 160. 160 times 5 is 800. So if I want to go to line 5. So what I can do is I can say this is the cell offset. So I'm actually just going to write in here 800 plus that.
Oh boy.
All right. So this will kick it down to, it should be row 5. So that's 160 times 5.
Okay.
So that should put me on row 5, which will be just below the stuff that's currently there. Yep, so there's my hello now. So that's 0, 1, 2, 3, 4, so this is the 5th row. That makes sense? And that's because we asked for, well, we didn't ask for anything. We just took memory that we decided was available. Now I'm pretty sure I'm gonna cheat here. Let's try to get this to break. Jack, weren't you saying there was a lower address that you had issues with?
Yeah, I tried the one that you had there, but with a 1 instead of a 3, and it just
All right.
didn't like that.
So we're gonna still be in. Oh, actually, that's gonna be extra bad because that's exactly where grub loads.
I think it loaded though. I mean, you can try.
Well, no, I get it, but it was used memory. It was already grabbed memory. So the OS loaded, then we tried to use it, because don't we have in our loader.s? It's not there. Oh, actually, it's in our. I think it's in our grub conf. This guy? No. No, it wasn't. Ah, right here. So, the OS should load right at 1 megabyte. So this is our setup for grub, for our loader.
Yeah.
So grub puts itself at 1 megabyte. So we probably could not have picked a worse spot to start. But let's pretend like we didn't know, right? So we'll come in here to kmain C. So now I'm just randomly deciding that, oh, it's safe to start at 1 megabyte for where our reserved memory is. I'm not going to change anything else. We'll come in here, we'll do a make run. It loads everything, you compile, everything seems like it's legit. And we get, actually it didn't even panic. It just doesn't work.
Yeah, I cleared out the whole frame buffer before I.
Oh, so you got an empty,
Yeah. So I don't know if that has a difference to do.
well yeah, you would have overwritten these if you're clearing out the frame buffer. So you had a blank screen?
Yeah.
Yeah.
Just replay what did you do to get to this point?
What I'm looking at right now, or the working point?
What are you looking at right now?
I decided that, hey, I don't really know what I'm doing. So rather than starting here, I'm just going to arbitrarily kind of start there-ish.
Because I'm at that point right now. Like that's where mine is up.
Yeah, well, but so, I mean, I could pick other numbers here and still be just as bad. I just changed my data space chart to a 1 here instead of a 3 here.
I'm just trying to figure out what was wrong with mine. And I think that.
Well, if you change it to a 3, that will put you clear of where grub loads.
No, you're right.
And now we'll be back to it working. All right. And what Jack had said is what he actually did is he did a clear of the buffer.
Loop through 25 times, 80 times.
Yeah. So what he did is,
You got the whole background covered then.
well, you could give yourself a colored background.
Yeah, that's what you'd have to do then, right? That would just reset what the background looks like.
Yeah, with nothing there, and just change the color.
Yeah.
Yeah, so I can write a function up here called like void FB clear, and have this guy take in no parameters. And what it'll do is it's going to say for int I is equal to 0, I is less than, what did we say? It was 80 times 25.
Yeah.
I plus plus, and then we'll say FB write cell at bucket I, and we'll go ahead and write the space, And we'll give it the color. Is there like a black? So black. Yeah.
Do we have to do I times 2 also for the first spot still? Because that's
Yeah, it will
the
be.
half sizes.
So then what I can do here is instead of offsetting at 800, we can just go ahead and do a FB clear. And then it'll clear our frame buffer. And then when we write the hello, it'll be in the upper left-hand corner, but not overwriting other things. Oh. So there's my hello. So that's how you cleared your buffer, right?
Yeah.
Yeah, so if you hadn't written, well, if I change my thing now to the 1000, this will show me nothing on a blank screen, which is what your output was.
It's so pretty.
Yeah.
It's so pretty now.
I will put that one in picture.
Yeah, it actually does fail. It's crashed. Yeah, it's crashed. All right. Gotta switch it back to 3000. There we go. All right, so does that make sense? So now what you might want to do is you might want to go ahead and have a write string. And what I did is I gave myself an option for an offset inside of my write string. So I can say I want you to start at bucket 800 or something like that, which would be the beginning of line 5 in my buffer. And you're going to write out this char pointer, which points to the beginning of a character array. And that's how long it is. So now what I can do is get rid of that. And I can say I want to write string offset of, and I'll show you how I got my 800. I got it 80 times 2 times 5. So 80 cells, 2 bytes per cell. I want to go down to row 5. That gets me an 800.
Okay.
So that's my offset. And then what am I going to write? I'm writing S. And then it wants me to pass it a length, so I'm writing it to length 5. So there's my hello on line 5. All right, make sense? All right, so now what if we did want to have our own memory manager? I've kind of said by our picture here that I have from 3 megabytes all the way up to, what would this be, 30, call it 31 megabytes, just to keep the math easy. And I'll just, give myself a little bit more stack space. So I'm going to, because based on the picture here, our stack is actually only like that big. It's super tiny in terms of K. Okay, but if I want to just keep it easy, I'll go from 3 megabytes to 31 megabytes. That's my available memory. Mm-hmm. All right, so how do I represent that? What's a memory manager? Think back to your 350 class.
Making pages.
Okay, so there was different approaches to how do you handle memory, right? All right, so what is the job of a memory manager?
So programs where they can translate where the program thinks it can actually put stuff to where it actually puts stuff.
Okay, so it would be a way for a program to ask the operating system. So the memory manager is one of the main functions of an operating system, right? And it would give us the ability for us to ask the operating system for a plot of land big enough for holding something, right? And so it would go out and it would go through memory, whatever that means, however we decide to represent memory. It would go through memory finding a spot that was allowed. Does that make sense? Okay, so if we think about memory as bite-sized buckets, sometimes in modern operating systems we think about it as bigger than that. We think about it as like 4 bytes or something like that because of the nature of the kinds of things we usually store there. But for us, let's just assume it's bite-sized buckets. Keep things simple. So if I have 30, what did I say? I'm going from 3 to 31. So I have 28 megabytes, right? 31, 30, 29, 28. So I have 28 megabytes of total memory. How many bite-sized buckets is that? So 28 megabytes times 1,024 kilobytes times 1,024 bytes. Oh, sorry. So 28 megabytes times 1,024 kilobytes times 1,024 bytes. So I have 29,360,128 buckets I'm managing. Right? So I have a collection of buckets in front of me if I'm the memory manager. Specifically in this case, I have just under 30 million buckets. Right? And I'm saying, you could ask me, you can say, I need 75 buckets. I'm going to give you I'm going to give you the address where you can use 75 buckets. So I need to go through my memory, finding a place in memory that's available, and then making sure there's 75 things after that. Does that make sense? And as soon as that returns true, that means I have that memory available. Correct? Okay, so that's allocating memory rather than hard coding memory. How would we write that? How do you represent memory if we treat that as an abstraction? So this is what my memory looks like. And we can represent this guy as $29,360,128 byte size buckets. So that's the number of bite-sized buckets that fills the green. And I want to have a function maybe called getMem instead of malloc. Okay, we'll call this guy getMem. And getMem will take in number of bytes required. That's what it'll take in. Now, I know I can support up to 29 million here, so I actually can do this with I do need a int, right? Because a short would only let me go up to 65,000 for an unsigned short. So I need an int, which will get me up to 2.1 billion. So I'll take an int number of bytes called getMem, and this guy will return the base address where that much memory can be used. And it will mark that memory as in use. Because both of those things need to occur, right? When I ask the operating system for 75 bytes of memory, I'm intending to use that memory, right? So I'm saying, here is the memory that I'm using. Go ahead. Well, here's the memory I need. I need 75 bytes. Tell me where that starts, and then mark it off so nobody else uses it. Is that going to be a helpful tool for us as we start moving towards writing our own system calls and things like that for accomplishing multiple things in our operating system at once? Not using the same memory over and over again? Go ahead.
No, I was just saying, but
So we need some different way to keep track of what we
Yep. So I need an abstraction. I need a way of keeping track of what I've used. Okay, so what's that abstraction going to look like? I know I have 29,360,128 bite-sized things. Okay, it's an array. Okay.
We know how that.
All right. Well, problem is if I have, it's going to be an array of what? What kind of things? Cat, dog, int, char, grapefruits. Well, we want to go with integers. So if I have 29,360,128 integers, how many bytes is an integer? 4. So divided by 1,024, divided by 1,024. So that array is going to take 112 megabytes of memory, and I'm in a 32 meg system.
yeah,
Do we need to know anything else besides whether it's loose or not? In the memory, because we could just use a bit then. That'd be one idea.
Could use a bit. How do I represent a bit? I don't know. C doesn't have a type for bits. Smallest I have with C is a
So we
is a byte.
we could bite no wood spot here.
Okay, so now we're in the same problem that an early operating system designer would be in, right? They're standing there and saying, okay, I have this much memory, and I want user programs to be able to ask me for some memory so I can make sure that they don't, that I can kind of keep them organized, right? You get this area for your program, you get this area for your program, that kind of stuff. But I need a way of marking memory as being available or unavailable. How do I do that? Well, we could create an abstraction, which is an array, potentially an array. But if we have an array that's going to hold bytes, and I happen to say that my memory is going to be bytes, that means I'm going to use the same amount of memory to manage my memory as my memory itself. Well, I have an option. I can then choose to give myself half the amount of memory. Since I'm going to require, so instead of it being 28 megabytes of memory, I can give myself 14 megabytes of memory using a 14 megabyte abstraction for managing my 14 megabytes of memory.
Doesn't sound
But possible.
yeah.
So how am I going to pull this off? I want to be able to I want my user to be able to call getMem. I want to be able to come in here. And I want to be able to say this. char s is equal to getMem 5 bytes. That's what I want to be able to say. Give me the base address where I can store 5 bytes. So right now we can say this is going to be a char pointer called getMem, and this guy is going to take in a num bytes. And for all we know right now, it's going to say data space start. There you go, buddy. You got 5 bytes of runway right there at the beginning. I didn't check anything. It'll work. You might do some damage to your friends, but it will work. All right, but we want this to work better than this. So instead of returning the base address of everything. Let's get specific. Is what we're really trying to accomplish there. So how do I pull that off using this picture? I want to find out where in here I have number of bytes available in a row. Go ahead.
So like, I don't remember exactly how this works, but I remember in OS there was segmentation.
Segmented memory is what you're thinking of. Yeah.
And then we went to
Yeah, so this is not even a chicken or the egg thing. This is a different thing. Yeah. Segmented memory allows you to wrap a base address and an offset into a single memory address. Which is fine. I mean, so the punchline here would be we can choose to let getMem return a segmented memory address, which we're not doing yet. We're thinking about this thing as just an array of memory, buckets in a row. We're not thinking of it as being segmented into different security parts and things like that. But segmented memory operates off, like if you ask for a memory address in user space, it will return the address. It'll give you a memory address, but that memory address is like an encoded memory address that starts off with an offset of where user-based memory starts, plus where your bucket is that we've assigned you in that user-based memory. Right now, we're just saying this is memory. We haven't segmented it. We have hard-coded segments. That is, OS gets that, Stack gets that, we get the rest. Does that make sense? So if we're managing this one resource here, which is 29,360,128 bytes of right off the bat available memory, and I want somebody to be able to ask me for a certain number of those bytes and for me to be able to give them values. How do I do that?
Really, just going in order probably be the easiest way to keep track. Don't know if it's the most efficient.
Okay, so when you say going in order, tell me about that. How might that work?
Well, you start at the very beginning of the unused space,
Mm-hmm.
and then you keep track of when you allocate memory, and you start from the spot that's the next emptiest, and give them however much memory they request. Move that pointer to the starting spot, and then
Okay. So that would probably work for a while, for right 28 megs of stuff.
Yeah, until you run out of space.
And so at that point, we haven't necessarily considered people giving it back. So at that point, it's like buying land, but you buy it, you keep it. There's we have no return policy, right? You want 65 bytes of memory, no problem. We start at the beginning of our rib roast, jump in 65 bytes, cut it right there, saying here's your memory. Next guy asks for memory, I'm starting right here. Because that other memory is dead to us. Even if they only use it for a second, they can't give it back.
What used rib roast?
Well, depends how hungry you are. If you're pretty hungry, it depends how used. For all you know, they put it on the plate and didn't eat it. It's still fair game. Well, yeah, I mean that's when you start going down a path of how desperate are you? Yeah. What stage of digestion was?
Food or Are you suggesting we go on a different route, like having the first bit of each byte being reserved for whether it's used or not?
I'm not necessarily suggesting anything.
Okay.
I'm asking.
Okay.
So his solution would work for a while, right? We could just say, hey, we have 28 megs of unused memory. I'll just start handing them out in order, and when we're out of memory, we're out of memory. What do you do then? Reboot your machine. Now you got a fresh 28 megabytes of memory to start handing out.
Then you run a helper function that clears out the memory that was used.
Or what you can do is you can just roll the dice, right? So once you hit your 28 megabytes, just go back to the beginning and just, they're probably done.
I'm pretty sure we talked about that.
They're probably done.
Yeah.
how could they possibly be using it this long? Go ahead.
So we couldn't have an array of bytes that we're using as bits, even if like we, had each one representing a different spawn number. So then it would be an eighth of the size of the whole thing. So
You could pull that off. You can do the math with to look at the individual bit for which thing you're in and try to make it work. So then instead of it being 28 gigabytes, it'd be an eighth of that in size. So still, it would take away take away overhead.
Mm-hmm.
What does it mean for a bucket of memory to be unused to us?
Oh, it's all zeros.
Are you allowed to store a zero at memory?
You are.
What does the byte 0 mean?
Oh, exactly 0 of that object is there.
So this is
We know.
now we're starting to stumble into this idea of how does comma separated values work. It's like, well, you can't have commas in your values.
Well, so what if everything, nothing there would be null then for what we're used to with other stuff? Is that accurate? Not really. Like.
Well, it depends. We get to define what null means in our language,
Okay. So.
or in our OS rather.
Like we all have.
Well, if it was a byte, it would be FF
Okay. Yeah.
because you need a nibble to represent a 15. We're gonna have it all zeros. And if it has a 0, it's unused. If it doesn't, it's used. I mean, that could work. What you've done, though, is you've then said that each of those buckets is not allowed to legitimately hold a 0. If you try to put a 0 in one of your memory locations, you are risking it being given away to somebody else because a 0 is considered nothingness. Well, doesn't have to be bad. Go ahead.
Could you split it up so we're working with 32 bytes at a time? You know what I mean? Instead of giving away 1 byte at a time, give away a larger amount and then do a bonus in bits.
Well, you certainly can, but then you'll have more, if you're thinking back to your OS class, more internal fragmentation.
Yeah.
Because you might only use a byte, and you have 4 bytes, so now you have 3 bytes of wasted space and 1 byte of used space. So I think for us, it probably makes the most sense for us to imagine this as a collection of bite-sized chunks for our memory, because we're going to be operating in bite-sized things for a while, or I guess possibly 2 bite-size things for some of our stuff.
Is there a way that memory's flagged, on the hardware somehow?
Oh, to flag it, you need something else to mark it.
Yeah, I mean, is there extra space somewhere that just isn't inside of memory? That's on the hardware side.
You could. I mean, now this is kind of we're in this game where we have to function the way that the early operating system writers, even today's operating system writers, have to function. How do we decide what memory is currently used and what memory isn't? How do we keep track of that stuff? Do you have an array that is a mimic of what memory actually looks like, and you just decide what's marked off and what's not? Then you can just mark it as a 0 or a 1, because those aren't the values. Those are just on or off, used or unused. But if you use the bits in place, now you're sitting in the position where you're like, okay, well, it has a 0 there. Does that mean not used, or does it mean dude wants to hold a 0? Which of those two is it? You gotta make a guess. Or you have to remove a value from the possible values allowed to be stored in your memory. Where if somebody does store that, it means off. It means not used.
You always do with SSDs, we have the voltage differences. But is there a
Okay, you want to write the C code or even the assembly code to test that? I don't think that's going to fly. Now we're talking about building another piece of hardware that's going to be our memory manager.
So, are we hearing for the assignment to be make your own memory manager? And that's what
Yeah.
we're just talking about different ways to do it?
Yeah.
Okay. Or are we making a decision in class on what to go
No,
with?
you can. I don't care what decision you go with.
What are we doing right now?
We're talking about what decisions might make sense.
Okay.
Probably coming up with a solution that would be a pretty good idea, but if you wanted to experiment outside of that, you could. So the most straightforward solution so far is probably we're going to have the amount of available memory. So instead of 28 megs, we're going to have 14 megabytes of available memory, and then give ourselves maybe the first 14 megabytes of our memory will be taken up by a 14 megabyte byte size array of bytes, array of chars
Yeah, isn't
that
there-
all hold zeros initially, that will get flagged to ones as we use stuff. What's the advantage of that solution? The advantage is, well, not just simple, but also we don't necessarily now have to limit our end user to the kinds of values they're allowed to store. They can put whatever they want in real memory, because we're going to have a second copy of this. If I draw the picture of it, I'll make that guy blue. So now it's kind of like that, right? Where we take up the first half of our memory with our memory manager. So this is an array of bytes, all marked as 0 at first, unused. And then this guy is the actual memory with offset of base address here plus 14 megabytes. Well, there is. Let's talk about this at the high level. So now our new starting point of memory is here. If I want to know if that first byte is available, I have to look at bucket 0 of this guy. If he's a 0, then this guy's available. If somebody's asked me for 65 bytes and I find the first 65 of these are available, I can then go ahead and mark these as unavailable, putting ones in here, and then hand out this base address. And then when somebody else comes in, I can then go through and assign the next chunk. That would even allow us to support deleting memory. When somebody comes back and says, I want to delete the memory starting at memory address, let's just say it's the base address, this guy. I want to delete that 65 bytes of memory. So it'll hand me that base address. We have to know how many bytes of memory did you request in order to free that back up, to switch these ones back to 0. So we might decide that our delete function initially requires the end user, not dissimilar to how in C arrays require us to keep track of, is that at 4%?
Yeah.
They don't require us to store values, or arrays don't know how to store their length. So instead, we can say, okay, you tell me what memory you're freeing. You give me the base address and how much memory you're freeing, and I can free that up for later. That's one way we can do it. Another way we can do it is we can decide to compress that to a certain extent, like you were mentioning, where now you're using maybe an eighth of it if you want to use it at the bit level, whether it's on or off. There'll be some extra math involved there, so some other computational overhead. I think that might be a reasonable way to start with our memory manager. Have there be overhead where we give up memory in exchange for storing stuff. I think is safely storing stuff, I think could be beneficial. As we get farther down the line, we might choose to do some file I/O stuff. We might choose to store our memory model in a file and maybe only read in part of that file at a time. So there's different approaches to this, but the idea is that we're starting off with this idea of I have this block of stuff that I need to manage, and I can either say, here's this special value that can't exist, and therefore therefore the first part of this is, or therefore I'm just going to mark in actual memory whether it's used or not, by storing that not allowed to use value there. Maybe it's a -1 or something like that. Does that kind of make sense? Okay, so for next class, come up with a solution for get mem where I can maybe get 15 or 20 chars, or 15 or 20 char pointers rather, for strings, and print them out, and it gives me different memory for each one. It's assigning legitimate memory somewhere in our available space. And you can pull this off however you want to pull it off. Go ahead.
You want that like solved, like
Working.
okay.
Yeah. So I've given you a starting point here. I've given you a starting point here, and I'll upload this to GitHub. Don't I have a Git thing in here somewhere?
No, not yet.
All right, well, I'll put this up on GitHub so you have access to my growing thing. But outside of that, you get to use your imagination for this. But try to put yourself in the role-playing position of, I'm an early operating system designer. People are asking me for parts of my memory. How do I give it to them? And what is it costing me? We don't worry about that in today's world. All right. Well, we are out of battery. I'll have to bring a charger in here. I do have an extra one.